Have you ever pondered over why a rubber band can stretch and then bounce back to its original form? Or why a paperclip can be twisted into a variety of shapes without snapping? These are all due to the mechanical properties of matter, the intrinsic characteristics that dictate how materials behave under the influence of forces. Take strength, for example. It's the maximum stress a material can endure before breaking or yielding. Imagine a bridge made of high-strength steel, capable of withstanding immense weight without collapsing. Or consider the spider spinning its remarkably strong silk into a web that captures its prey. Then there's elasticity, the ability of a material to return to its original shape and size after deformation. Picture a rubber band stretching under force but regaining its original shape when released, or a spring compressed under pressure but bouncing back when the force is removed. And don't forget about plasticity, the ability of a material to deform permanently without breaking. Think about Play-Doh, malleable enough to be molded into different shapes and then retain those shapes. Or metals like lead and copper, which can be bent or hammered into new forms without snapping. Next up is ductility, showing how a solid material can be drawn into thin wires. Gold, so highly ductile, can be hammered into extremely thin sheets known as gold leaf. And copper wires, so prevalent in electrical applications, owe their usefulness to their ductility. Malleability, on the other hand, refers to the ability of a solid material to be flattened into thin sheets. Aluminium foil, rolled into thin sheets for food packaging, is a prime example. And silver, often used in jewelry and decorative items, is another malleable metal. Then there's toughness, the ability of a material to absorb energy and resist fracture. Nylon, tough enough for ropes and parachute fabric, and polycarbonate plastic, tough and transparent enough for bulletproof windows and safety glasses, are perfect examples. Finally, we have hardness, the resistance of a material to surface indentation or scratching. Diamonds, the hardest natural material, are used in cutting tools and abrasives, and steel, harder than wood, proves a better choice for tools and structures. Now, let's delve a little deeper into stress and strain. Stress is the internal force per unit area acting on a material due to an applied load. The stress on a bridge cable, for instance, increases with the weight of vehicles crossing it. Similarly, the stress on a bone increases during exercise or physical activity. Strain, however, is the deformation or change in shape or size of a material relative to its original dimensions due to stress. A stretched rubber band experiences longitudinal strain as it lengthens, and a bent beam undergoes transverse strain as it deflects. In the realm of elasticity and plasticity, materials that exhibit perfect elasticity return to their original shape and size when forces are removed. But real materials often have an elastic limit, beyond which they deform plastically to some degree. Springs and rubber bands are nearly elastic within their elastic limits, while steel beams show some elastic deflection under load but may also have some permanent bending if overloaded. So, to summarize, the mechanical properties of matter determine how different materials behave under the influence of forces, from the strength of steel bridges to the elasticity of rubber bands, the ductility of copper wires to the toughness of nylon ropes. Understanding these properties helps us harness the potential of these materials in our everyday lives. By diving into the world of stress and strain, elasticity and plasticity, we gain a deeper appreciation of the hidden mechanics shaping our world.